will talk about the porous polymers. I choose this topic because nowadays, so you will see, so there are different kind of porous polymer, and they show really so very nice properties and can be used in huge different areas. We have only 90 minutes. .5 hours, of course, it's not enough if you want to know the details of the topic. So that's why. So in this case, I just want to introduce you. So if you want to learn after the lecture, so you can look. So one of the book. So this is book from Silverstein. So it's a very good one. So I do recommend. So they write this porous polymers. And of course, you have also possibility. There are 2 very nice review articles. So the first one is from Professor Matiaszewski. So he's one of the most, so he's a synthetic polymer scientist and from the founder of ATRP method. So, and of course, he's really an expert on this topic. So you see, so he is the first, I think this is the first very well written review article on porous polymers. And recently there are also some new coming. So that's why I also recommend another one. So, but this is more connected like also to specific applications. So, you know, on one side, the basic, what is porous polymer, how you can design and synthesize your polymer. On the other side, of course, you should always connect the functional group, connect the structure with the specific application. So that's why this is also a very good example. So the question, when we talk about porous polymers, of course, you will first ask here, so what is porous materials? Why we need porous materials? Here, I just want to show you some nice, actually, I do not want to show you some nice photo or nice image, but just give you some example or give you good impression what we can do with porous materials. On the left side, so you see, so this is a kind of silica aerogel. So of course, this is very porous material. And you see, it shows excellent thermal isolating properties. So even you have a fire under, so it will not really to burn your finger on the other side. So it's really a very good insulator material. And of course, if you make a kind of very porous, here is carbon, so this is made of carbon. So you can also have a extremely ultra light solid material. So based on such kind of porous structure. So this is also nice one. So from the group of Gao, so they are very good at this graphene based carbon aerogels. And actually this morning I also just saw their group published one science paper this week also to study these graphene fibers. And they found the graphene fibers, they are like retunable materials, so they can be sponged during the bending, and then afterward it will be self-healing. And another on the right side, of course, this is a very popular example. Maybe you also have it or use it in home, so at your home. So this is based on, of course, active carbon. So it's a kind of filter and can purify water efficiently in this case. You can also find bunch of porous material in the daily life. For example, so our bread or cakes, if it's not porous, then it's so hard, and you will say, this bread is, this cake, tastes not good because if it's not porous. And of course, there are also some other very good applications, this like this nature lattes also paper, sponges, clay is also kind of porous material, and so on. So you can find this porous material everywhere in your daily life. And before we talk the detail about the porous polymers, I just want to give you some basic definition or basic characteristics about the porous material. So first of all, when we talk about the pores, so it does not mean it's a kind of very defined, because sometimes you look into paper, they draw porous material with really nice like holes or spherical holes, but actually it's never like this. So the pores can either be cavities or channel-like pores, or it can be also interstices. So the pores will be in a different, actually not defined shape. And when we talk about the pore volume, so it means the volume of all the pores. Of course, pore size is one very important parameter if we talk about the porous material. And here, when we talk about the pore size, it actually may on the pore lines. So it means the distance, yeah, of the two opposite walls of the pores. And of course, so porosity is also a very important characteristic for the porous material. So the porosity means the ratio of the total pore volume to the total volume of the material. So this is called porosity. And on the other side, of course, you have also surface area. So the surface area is defined as the accessible or detectable area of the solid surface. This is called the surface area. And so later, when we look into different examples, I will always give you some specific surface area of some porous system, and you will see. So I just give you here a first impression. So the average surface area of one adult or one person, yeah, human being, so it's around 1.6 to 1.9 yeah, square meter. And later you will see how huge will be the surface area of such kind of nanoporous or mesoporous material. And then you have the definition of the specific surface area, which is defined as a surface area per unit mass of material. So normally you have like square meter per kilogram or square meter per gram. So often it's square meter per gram is used as the unit for the specific surface area. And with this, you can, of course, yeah, compare the surface area or the porosity of different materials. And the last will be the true or apparent density. So this means the density of a material. So for the true is exclude, and for the apparent is include here, the pores and inaccessible pores. Very important, I just give you here, when you would like to describe a porous material later, yeah, if you will work on this topic, these are the 4 very important parameters you need to know for your material. So one is the pore size and pore size distribution. The second will be the pore volume. And the third is the pore porosity. And the last will be the specific surface area. So this are the 4 key parameters when we want to describe a porous material. Of course, there are different kinds of pores, and according to the definition from UPEC, they define the pore size region into 3 different pore type materials. So when the pores, they are smaller than 2 nanometer, it's called microporous material. So in this case, you will have a huge specific surface area. So normally you will have the specific surface area more than 1,000 square meter per gram. And some examples, so it will be like active carbon or MOFs. So these are typical microporous material. And if you have the pore size between 2 and 50 nanometer, it calls mesoporous material. And in this case, you will also have very appropriate specific surface area. Normally, it has in the range between 100 to 1,000 square meter per gram. As typical example is mesoporous silica materials or mesoporous metal oxide, carbon, and so on. And when we have the pore with a size larger than 50 nanometer, then it called as a macroporous material. And for this macroporous material, normally you have quite limited specific surface area. So it's normally smaller than 100 square meter per gram. And in this case, some example will be like membranes or forms or resins. So they belong to the macroporous material. And if we look here, so a scheme for a porous material, so how it looks like when we talk about the micropores, mesopores, or the macropores. So you will see, so for the macropores, it's really in a kind of macroscopic structure. And then you have in between such kind of mesopores. And if we talk about the micropores, you need to zoom in, due to scale. So it will be really a very fine porous structure. And of course, so the design concept for a kind of high performance porous material, here we need always to think about a good balance between the surface area, so specific surface area, and with their diffusion kinetics. Because of course, when you have very, small micropores, you have a lot of, so diffusion barrier. If you have like a macropore structure, you have very fast diffusion kinetics. So this you always need to keep in mind. So after we introduce, so what is porous material and how you can define different kind of porous material, then we will talk about how to synthesize. So later we'll see all my lecture will be formed in this way. So I give you a short introduction about this topic. Then of course we will introduce the different approaches, how to synthesize such kind of material. Then in some cases we'll also introduce if you need some specific characterization methods, to study or to analyze such kind of material. And in the end, of course, I will always give you some example so you know how you can use those possible application for such kind of material. So first of all, we will talk about the synthetic approaches to porous polymers. And normally, so these are the three most often used or the most three classical synthetic approaches to synthesize porous polymers. One is the templating methods. The second is self-assembly methods. And the third will be the direct synthesis methods. So I will go detail with these three methods and also give you some example. So for the templating methods, you can know from this definition already. Of course, you need a template. So you use a kind of material as a template. So then, so this template have already such kind of porous structure. Then you will filtrate your synthesized polymer into such kind of porous structure. And then in the end, you can remove the template. Then you will get a kind of porous polymer in the end. So the advantage for this approach, you can see, So the concept actually is quite simple. So it can be widely applied for different kind of polymers. And of course here depends on the porous template you will use. Yeah. So normally so it's possible for you to get a kind of uniform pore size and also nano pore size distribution of your final products in this case. The disadvantage for this method, you see, so we need a kind of template. And of course, it will be nice to have a well-defined template with this porous structure. Then, of course, you need time. So it also costs not only time, but also chemicals and all this. So it's quite complicated. So to have this template preparation, and also after that, you need to remove the template. Yeah. Then it requires also additional time and also give you additional cost there for the remove of the template. And so this is a disadvantage for such kind of methods. But I should say so in the lab scale, so of course, yeah, so this is one of the most simplest way you can synthesize porous material. I give you one example by using this templating approach. So in this case, so the authors, they have used this silica nanoparticle as a template. And then they use two monomers. And so they mix these two monomers. So one is this vinyl imidazole, and another is vinyl benzene chloride. So they mix this together and do the polymerization. And in the end, so after polymerization, you will get a kind of hybrid, polymer silica hybrid. In the last step, so of course you need to remove your template. So then they're using sodium hydroxide to like strong base, to etching silicon. So finally, they will get such kind of mesoporous polymer materials because they use this imidazole. So this is a kind of anion liquid monomer. So finally, they get a kind of mesoporous polyanion liquid. And you see here, yes, the concept for the generation of pore is so you can use any of a meso particle, which has a specific shape and size to use them, to generate or to make pores. And after that, of course, you need to dissolve away or to etch them away to get the final porous structures. And in this case, of course, such kind of silica, so mesoporous silica particle is the most often used because you can buy it commercially and they can offer really different size of silica particles. So this is one of the most often used method. And as a second approach, so it's called self-assembly methods. And so self-assembly methods, so in this case, they are mainly based on the Porous polymers because Porous polymers are a kind of very nice material which can really, so by self-assembly to form different kind of structure, and then by selective etching or dissolving, you can generate pores, based on this self-assembly of Porous polymers. And the advantage for this method, because self-assembly of Porous polymers, this is a very well-controlled process. So that's why by this method, you can really have very well-defined pore structure. And the disadvantage for this method, you see, you need such kind of Porous polymer. You can either, of course, so synthesize such kind of Porous polymer by yourself, but then you need additional, knowledge, to know how to synthesize, because here the molecular weight and the molecular weight distribution of the bulk polymer is a very crucial parameter. So if you do not have well-defined molecular weight distribution of this bulk polymer, the structure of the self-assembly will be not well defined. So that's why it's very crucial to have a good quality of the bulk polymer. And of course, you can also, for some of the bulk polymer, you can buy it. So it's also commercially available. But I should say, so the price of this bulk polymer is very expensive because we also work on this topic. And so we use this, later I will also show you one example. So we're using polystyrene P2VP bulk polymer as template or as copolymer used in. And for this, so it costs, so 1 gram of such kind of bulk polymer, €300 or $300, yeah, because we bought it from America, so a company from America. And what even more expensive is because now you need to also give a tax, yeah, so because it's kind of import, yeah, from USA, then we need to give additional 200 euro, yeah, for 1 gram of that kind of bulk polymer. It's really expensive. However, you can get really very beautiful structure. So you will show, I will show you, yeah, the slide, you will see it. So here I give you, I would like to give you 2 examples. So this is first example. So these authors, they use, so actually 2 different, so the first, yeah, so this is their system, so mix. This is one polymer system. So you see, so for this polymer, they have PLA as a main chain. Then on this side, they have this raft agent, yeah. So then you can do the raft polymerization based on this functional group here. And then they mix them with the secondary polymer. So this is PO. So then they mix this together and they add additional monomer inside. So they use this S is styrene monomer and DVP is divinyl benzene. So this is the cross linker. So you have 2 double bond on this benzene. So this is a cross linker. Then they mix them together because we have this raft initiate agent here. So they do the raft polymerization and then will form a kind of bulk polymer. So this is PLA together with polystyrene, so a kind of dibulk polymer, and mixed with PO. And PO will aggregate to form such kind of macro domains. And then after that, they do the basic aging. So by this aging process, the PO will be dissolved in aqueous solution, and then PLA will be deaggregate because PLA is well known as a biodegradable material, so it will be degraded. And so you will generate, in principle, 2 different kinds of pores by this simple aging process. So one is macro pores, which are from the PO domain. And the second will be these mesopores, which are generated by the degradation of this PLA domain. So it's very clever methods, yeah, to generate such kind of hierarchical, yeah, porous polymer. Second example, so this is what we have done in our lab. And so we want to generate such kind of porous particle which have the tube channel and embedded with a gold nanoparticle, yeah, in such kind of tuberous channels. And for such kind of particle, we're using the polystyrene P2VP. So because polystyrene P2VP, they will self-assembly into such kind of well-defined pattern with a kind of micro particle structure. You have a pattern here, particle. And then we do use a selective swelling process. So we choose ethanol. So ethanol is a kind of a good solution for P2VP, but not a good solvent for polystyrene. So that's why, so we will generate a kind of porous structure on this pattern here, spheres. So you will generate a kind of porous particle based on this polymer self-assembly. And of course, yeah, you can always design your system even more complicated. So because we have P2VP, so P2VP, they can have a complexation with gold precursor. Then we use UV irradiation to reduce the absorbed gold precursor. Then the gold nanoparticle will be generated into such kind of porous polymer spheres. And we can even coat it with a thin layer of polydopamine. So you can use dopamine as a monomer, then it will so it's a kind of self-oxidation polymerization if you have a tris buffer as a reaction medium. So you will keep the pH of this reaction medium at 8.5, then dopamine will be polymerized into polydopamine. So you will get kind of polymer coated with polydopamine. And then as a last step, because polymer, so this is polystyrene P2VP, and THF is a good solvent for such kind of polydopamine, for this polystyrene P2VP. Then you can generate additional, so a kind of porous structure for polydopamine, which you have gold nanoparticle embedded in this channel. So this actually you combined two different strategies. So one is self-assembly of bulk polymer. Second is this templating method. Then you can get a very nice and complex structure on such kind of polymers. Then so the third method, so of course, so you can also use a direct synthesis method to synthesize porous polymer. And most often, so this is divinylbenzene. So you can have divinylbenzene using THF as a solvent, then you do the polymerization in the autoclave, then upset, you can so evaporate the solvent of THF. Finally, you will get a kind of monolith based on this divinylbenzene. So it's polystyrene with double bond actually. And so you see here, the procedure, so actually the fabrication process is quite simple. And of course, it's possible, to do such kind of process in large scale, because compared to the methods, especially on such kind of bulk polymer methods, you see here, so here we do work on milligram scale. So it's very difficult to upscaling the whole process here, I must say. On one side, of course, is extremely high cost of the bulk polymer. On the other side is this self-assembly as well as the later, so this select swelling process. So this is all well-defined process, and you need to do really in milliliter scale. So it's difficult to upscale the process. But here, this is easy for you to upscaling the synthesis. But the disadvantage for this method, so you can see already the whole process here. So actually, there's no, how to say, clear strategy in this method, how you can control the pore size. So this is actually random controlled, I should say. So the disadvantage for this method is you do have a poor control of the pore size. I also give you one example on this method. So these authors, they use a kind of polyanion liquid. So the polyanion liquid is based on, so you see they have this imidazoline with a cyan group, and this X is the counter ion for this polyanion liquid. So for the counter ion, it can be quite different ion. You can use bromide, BF4 or BF6. So you can choose different counter ion, and using another, so PAA, so you can mix them together, and then to do the treatment with in ethanol with ammonium, and then by the drying you will get a kind of meso together with microporous polyanion liquid nanoparticles. And from the BET, so this is nitrogen absorption desorption methods. So they show the typical curve of kind of meso and microporous material, and the specific area can be around 310 square meter per gram. So these authors, they find a good way to have a kind of nice methods. So it's easy. You just mix and have the polymer together, so can be scaled up. Another example for this direct synthesis is so based on these porous organic cages. So this is also very, how to say, hot topic in the moment. The advantage here, actually, you can see, so you buy so the combination of different well-defined these organic cages. When you can really packing them together, you will have also well-defined porous structure based on this unit you have chosen for the synthesis. And also the advantage here is you see, so because these are all this depends on, of course, there's a structure, so molecular structure you will choose, but in all of the cases, so you can choose this acute or conjugated chains, and with a defined pore structure with like C8 or C12. So you will have really a very defined pore structure in this case, which around 1 nanometer. I also give you one example on this. So based on these covalent organic frameworks, so you can also do the direct synthesis. So you use these two monomer or molecules, So one is based on this triazine, and another is based on this TPD. And then you use this also. This is also kind of autoclave reaction, And you see, so you need really a very long time. And finally, you will get such kind of curve structure. So this is only one unit. So this is a computer simulated. So you will see, so this is only one of these porous structure. So you will get a kind of very nice organic porous material. And each of with this very defined this pore. And from the gas absorption desorption method, so you can see here they get very well defined pore, and it has a diameter around 1.5 nanometers. So this is like one of this pore size. And in this case, so you have this microporous material, and from the BET measurements, they have the specific surface area more than 1,000 square meter per gram. And so here, I just want to say, so I take this example from Professor Arnold Thomas. So he's from TU Berlin. We work together, so we use this as a very nice additives for the all solid state battery system. And his group is also one of the pioneer group from Germany working on such kind of well-defined organic porous materials. So after the introduction, so you know there are different approaches to synthesize porous polymer materials. Then of course, actually by the introduction of different example, I also show you some data. So you need to, of course, to characterize your material after synthesis, because you need always to demonstrate or to prove. So the material I have synthesized is really a kind of porous, it has a porous structure. So what kind of methods you can use, to characterize this specific, so such kind of porous polymers. And so I will mainly actually talk about the gas sorption, because we will see, so for every paper working on the porous polymer materials, they must show this gas absorption and desorption curves. But of course, so electron microscopy is also one of very powerful methods. However, here it depends on the pore size, because the resolution of the electron microscopy is quite compared to the pore of your materials. And in some cases, so the resolution is still quite limited. So I just give you some example. So normally, of course, so you can use scanning electron microscopy or transmission electron microscopy to describe or to characterize your porous structure. So in this case, so if you have a kind of macropores, because for macropores we do have really very huge pores, like more than 50 nanometer, or it's even 100. So in this case, this also they have like micrometer size pores. Then of course you can use a scan electron microscopy to study the porous structure of your material. But in some cases, you will have very defined like mesopores around 2 or 10 nanometer. Then by electron microscopy, scan electron microscopy, then it's not useful in that case, because the resolution of scan electron microscopy normally is quite low. And then you need high resolution TM. So in this case, this also have used high resolution TM, so they can observe this well-defined small pores, so around 10 nanometer, so such kind of pore structure. However, if you have even smaller pore size, like 1 nanometer, these MOFs, then it's impossible actually to be started using electron microscopy, because the resolution is not good enough. And on the other side, of course, depending on the structure, so I give you one example here, because here you see it's all carbon. And so carbon have very low contrast if you do the electron microscope, because you need the temp grace, and the temp grace normally you have also carbon film. So in this case already, so it's difficult for you to have a good contrast with such kind of porous polymer. And another thing is, so you have here, you see this conjugated structure. So they are very sensitive under, by electron microscopy, you always have this electron, so the beam irradiation. And then these structures, they are very sensitive to the electron beam irradiation. And so that's why actually during your taking the image by electron microscopy, actually meanwhile you destroy the sample in some degree already. So this is a very difficult task. And actually, so we have managed, so I did not show you, but we have a specific chapter on the electron microscopy, especially on this cryo-electron microscopy. So recently, so we have managed, so also working together with Anna Thomas, so we're using cryo-TM and to help them do visualize such kind of sectonome porous structure in the nanometer range. So next time I can show you these nice images. So another example I want to show you here, so if you have like a kind of mesopores, not really in 1 or 2 nanometer range, then of course this electron microscopy is a very good opportunity, because here you can even do the 3D tomography using electron microscopy. And this also, so we have done also in our lab. So in this case, so this is a TEM image normally you take for your porous. This is used Porous polymer. So this is a porous particle based on the selective swelling of the self-assembly Porous polymers, and it can form such kind of porous spheres. And by TM, so for the TEM, you just take one image. But for the electron tomography, so if you want to get a kind of 3D imaging of your particle, in principle, so you can always tilt the angle of your TEM grids at different angles. So you see, so we take image at different angles, so from -60 to 60 degrees. Of course, here I just show you a few examples. So in practice, so actually we take the image at every 2 degrees. So you can imagine how many images we should take to get a final, like a series of such kind of particle image. So you tilt your TEM grids at different angles and you take the image. And by computer resumption, so you can get finally a kind of 3D image of the porous template. So finally, so the computer will help you to generate the 3D image. So you see it's do like a porous, so material. And of course, with computer reconstructing, you can even ask so I want to see the cross-section of this particle, so you just cut it here, or you can also to tune your particle to see at different views, so like a surface view or the top view. So in this case, so you can always like to tune with the computer. So it's really a very powerful method, and to visualize your particle in 3D tomography range. So of course, so the gas sorption characterization is one of the most important and useful method if you want to characterize the porous structure of the porous materials. And here, so most often, it's the gas sorption methods, it's based on the BET theory. So that's why you will see in some papers, they describe so based on the BET measure test or BET measurement, but actually it's not a BET measurement. It's a gas absorption desorption methods. BET is only a kind of theory. You after the measurement, you will treat your data, and so the BET actually is from the name of three professors. So this is Brunauer, Emmett, and Taylor. So these are the three professors. They actually have developed this kind of theory to describe the specific area and the pore size of the porous material based on these absorption methods. So in general, the BET theory, they explain the physical absorption. So here it's very important, So it's based on the physical absorption of the gas molecules on a kind of solid surface. And it serves as a basic, as one of the most important methods for the measurement of the specific area of the porous materials. And so in principle, the standard BET analysis, they normally is performed or conducted at the burning temperature of nitrogen. So you see you need 77 Kelvin. So here it's like minus 200 degree Celsius. And it's also a kind of theory. So for the Langmuir theory, so it's based on the monolayer molecule absorption. And for the BET theory, so this is based on a multi-layer absorption. So these are the three assumptions for the BET theory. First of all, the gas molecules, they physically absorb on a solid in layers, infinitely. So here, so the gas molecules, they only physically absorbed on the surface. And second, there is no interaction between each absorption layer because BET theory is based on the multi-layer absorption. And then for each layer, so this Langmuir theory can be applied to each layer. So these are the three assumptions for the BET theory. Then you see, so if you have chemical interaction between the molecules with your surface, then this theory or this method actually is not anymore useful. You cannot use it anymore. So here's the equation, based on the BET theory. So in principle, you have this equation here. And so when we look into this equation, so it looks a little complicated, but if you look into it, actually not. So for the P, so this is the partial vapor pressure of the absorbed gas and in the equilibrium with the surface. So of course, at the temperature where you measured, so as we mentioned, so it's like in the liquid nitrogen, so it's like 77 Kelvin. And then for the P0, so it's the central-ated pressure of the absorbed gas. And then we have the parameter, so VA. So VA is the volume of gas absorbed at the standard temperature and pressure. So this is VA. And then for the VM, so VM is the volume of the gas absorbed also at standard temperature and pressure to produce a parent monolayer on the surface of the sample. And then we have the constant C. So C is a kind of dimensionless constant, which is related to the enthalpy of the absorption of this absorbed gas on the powder surface. So C is a kind of constant. And so for the BET, so normally for the gas absorption, desorption, so you do what you have to do is, so we can measure P, so over P0, so this is the partial pressure, and so VA is you measured, so when you draw the curve, so use this as Y axis and this is axis, then you will get a kind of linear, so you treat your data with a line. And with the slope of this line, so you will get this. And the intercept of the line, so you will get this. Then with this, of course, you can calculate the constant and this for absorbed volume of your gas. And so here is the typical, so for the different kind of porous material, so when you measure this absorption and desorption measurement, this is how it looks like, how the curve looks like. So if you have a kind of mesoporous, so you normally looks like this. And if you have a non-porous, so in this case, so it will have like several steps. And important is how mesoporous, material looks like. So you see, so you will have a kind of historic, for the mesoporous. So this is just for your knowledge, how it looks like. And very important, what we can get here from such kind of gas absorption test or gas absorption experiments. So this is a typical gas absorption curve we can get. And then depending, so here it's a kind of, as we see already, so this is typical, mesoporous curve. So for the mesoporous material, so we can use this BZH it's a kind of methods. So you can fit your data and to get information about the pore size and pore size distribution of your porous material. However, so this BJH method, this is only suitable for the mesoporous material. And if you have a kind of microporous material, then you should use different methods. And so I just give you, so for the microporous material, so you need this density function theory method, so DFT methods to describe your curve. Then of course your curve will be totally different like this. Yeah? So as the last part of our lecture, so as I mentioned, so the porous polymer, they show a lot of interesting applications. So depending on their functional group and also depending on their porous structure. So they have been used here. So I just give you examples. So these are most often used area. So of course, yeah, since this is kind of porous material, so they are well used in separation science. So it can be used as kind of porous polymer membrane or absorbents. And as a membrane, so here for this separation science, and of course, yeah, so you do can like to separate the oil with water, so a kind of specific water treatment membrane, yeah. So this is often used. And of course, yeah, so since you have a porous structure, so it means you have a huge surface area, especially on this mesoporous and microporous material. So in this case, of course, yeah, it can be used as a supporter to absorb a catalyst, yeah, on such kind of huge surface area. So in that case, they can be used as a supporter for catalysis. And so of course, yeah, so they have been also widely used in energy field. So for example, so for such kind of porous polymer, it can be used as a membrane for fuel cells. And they can be also, because you have huge porous structure, so it can be also used for the hydrogen storage. And recently, we also use this porous polymer, yeah. So used as a electrolyte, yeah, for the oscillator batteries, and also so with this polymer you can use as a template and to generate specific functional materials which can be used as an electrode for battery application. So this I will also introduce you later when we talk about this battery topic. And of course, yeah, so they can be also used for biomedical applications, because in this case, yeah, so when you have such kind of porous polymer, and it can be used for like tissue engineering, drug release, yeah, you have this process. Of course, you can use absorb the drug and then release, yeah, and for also other applications. So this is also like a typical overview you can see already. So can be widely used for different kind of application. And today, so I will give you a few examples what we can do with such kind of porous polymer. I give you, I think, 2 examples. So one example is, again, so it's based on this porous polyionic liquid. So in this case, you mix this polyvinyl imidazole, and so here you can use counter ions. They use TFSI as a counter ion, and they mix it with this molecule, because here you have this acid, and when you mix it and the acid will react with this ammonia, then it can generate some pores in the final powder. And so you can see here, so for this polyene liquid, you can get a kind of specific area around 250 square meter per gram. So this is also kind of mesoporous particle. And then they use this, so for the absorption of dye molecules. And you can see, so for the Pierce material, so this is colorless, so it means you can absorb all the molecules. And for SBA, this is a kind of mesoporous silica material. SBA 15, so this is also commercial available. So you see, so here you have this very strong color of this methylene yellow. And for the active carbon, you also see it's better than this SBA, so the mesoporous silica. But however, still, so compared to the Pierce porous particle, so the Pierce porous particle shows the best absorption ability in this case. Another example I would like to show you is, so you can, of course, use this porous polymer as a kind of support for catalytic applications. In this case, so you can, again, use this coriander liquid, and when you mix it with PAA, and similarly, so you can have this acrylic acid group, and then the acid group will react with ammonia and generate porous structure in the final powder. And so you can generate a kind of micro and mesoporous polymer, which has a specific surface area around 300 300 square meter per gram. Then you can load such kind of porous polymer with, in this case, this author, they use this copper. And they choose copper because copper is a kind of catalyst for the oxidation reaction of the organic compound in this case. And they have C, so you can see, so by using this, so there are different applications. So you can see why you use such kind of porous polymer as a supporter or as a carrier resistant for the copper catalyst. The reaction, so the catalytic reaction show much higher conversion and selectivity compared to this B and C. So these are without, so without this polymer, so you see they show much less catalytic conversion and very much less conversion in this case. So it means so these kind of porous polymer, they can be also work efficiently as a supporter or carrier resistant for the catalyst. So then I will have this take-home message. So for the key points from our lecture today. So this actually I want to ask you after our lecture. So how to classify porous polymers according to the pore size and diameter? And I hope, so you can answer this question after this lecture. And the second will be, so could you please list at least 3 parameters which are used to describe porous materials? And so the third very important here, so what is called so this BET equation, and what is it used for? So the next, so according to the UPAC definition, how does a typical mesoporous polymer looks like in a gas option isotherm? And how does a typical mesoporous polymer looks like in a gas option isotherm? So then the last, so if so you complete a kind of gas option test and with this gas option curve, by which method you can determine the pore size distribution. And of course, yeah, here, keep in mind, so it depends on the pore size. So for the micropores, you use actually different methods. If you have the like mesopores, so there are different methods to determine the pore size and pore size distribution. So I hope so after the lecture, so this is like the key points you need to learn. And I must say, actually, this is quite important and basic knowledge. And I'm sure, because I have been so many times with the defense, not only for the master also for the PhD defense, this question really it comes nearly every, I think, defense. So they will come from this. So because this porous material is really one of the often used or direct system that you need to know the BET and these gas option methods. So with this, I think so I have been through all this slide of this topic today. So is there any question from your side? Yeah. Yes, please. Yeah. Sorry again. Yes. You mean the pore size? Moment. I will try to share again. But actually, it do depends on the system. I hope you can see the slides again. Yeah. Good. So I should say, so this templating method, so this is one method you can synthesize the material, so the porous material at a very broad range of the pore, because it depends on the template you use. Of course, you can always, like if you use silica particle as a template, so you can buy the silica particle from nanometer, so 10 nanometer until 100 nanometer. So in this case, you do have the possibility to synthesize this porous material at different pore size. So this templating method is one of the most actually popular used methods. And you have a very good possibility to synthesize porous material at different range. And for the other methods, like this self-assembly method, so you will see, because this is all based on this Porous Polymer self-assembly. And in this case, so this Porous Polymer self-assembly is normally at mesopores range. So also here, you can see. So normally we have a kind of pore structure. So in the mesopores range, so around 2 to 50 nanometers. So these are often the pore structure you can achieve by such kind of assembly methods. And for the synthetic approaches, so here also depends on the system, but I should say, so here normally you have always like the mixture of different pores by such kind of methods, because you see here, actually you do not have a kind of control, a real control, So normally you can get like a micropore together combined with mesopore, so in this. Then, so depends, it do depends, on the application of your particle or on your material. So you can always choose different methods. Or you can even, as I give you the example, you can even combine the different methods to have a better control on the final structure of such kind of porous materials. I hope I answer your question. Mm-hmm. So I do not hear there's any further questions. So I wish you a nice weekend. And so I think so next Thursday will be the national holiday. So that's why we have Friday also. We do not have lecture actually on next Friday, because I think most of people will take holidays also on Friday. So we also have a kind of long weekend. Then we will meet again, yeah. So week after. And then we will talk about the conducting polymers on that. So good, yes. And so have a nice weekend.
Thank you very much.
Yeah, bye. So it's sunshine again, so it's really strange weather.
It is. It is. Thank you.
Yeah, bye.